Welcome to Mission Control, everyone. I am your flight director, and today we are initiating a high-stakes explainer. We're diving deep into the Cambridge AS and A-level mathematics syllabus, specifically targeting the 9709 parameters. Our mission objective? Vectors. We are locking in on vector notation, addition, subtraction, and scalar multiplication to ensure absolutely zero margin for error. Down in the telemetry bays, I've got my top crew with me. Alex over on propulsion systems, who tends to overload us with raw data, and Sam on navigation, who is incredibly fast, but sometimes misses those critical boundary coordinates. Together, we're going to guide you through this launch. Okay, let's strap in, power up the console, and secure those marks.
I want to start with a hard truth from the flight logs. Quote, most students lose easy marks on vectors, but after this explainer, you won't be one of them. Listen, in the realm of Cambridge mathematics, vectors really should be a highly reliable source of marks. It's a stable system. Yet every single exam cycle, we watch candidates bleed points. Why? Because they treat vectors as these isolated little calculation blips rather than a fully connected, conceptual framework. Our primary directive today is to establish a zero margin for error trajectory for you. By the time we finish this flight analysis, you will know exactly how to engineer a flawless exam response, avoiding the catastrophic failures we see year after year.
Let's quickly verify our pre-flight checklist on the main monitor. We are going to cover core vector principles, engineering the flight path, the method mark lifeline, hazard evasion with an interactive sweep, and finally our post-launch checklist. All systems are go.
Act 1, Core Vector Principles. We are officially calibrating the launch track.
Right now, I'm pulling up the official Cambridge assessment objectives on the main console. They break down their expectations into specific cognitive domains, which act as the varying altitudes of our flight. Down at the lowest atmospheric level, we have knowledge and understanding. Alex, our propulsion engineer, loves this part. This is your raw fuel. It's knowing how to accurately express a vector, or remembering the basic foundational rules of vector addition and scalar multiplication. But here's the reality check. Cambridge examiners expect a lot more than just raw fuel to reach orbit. You have to break through to application and analysis. Top-performing candidates exhibit a connected conceptual understanding that transfers seamlessly into completely unfamiliar contexts. You must be able to apply scalar multiplication directly to complex geometric proofs or analyze vector subtraction while navigating three-dimensional space. That's how you break gravity.
So what actually powers that breakthrough? It's the theoretical architecture of vectors, which rests entirely on precise definitions, causal relationships, and integration with other syllabus areas. The principal examiner reports highlight a massive trend here, flashing red on our dashboard. Candidates who reference cross-topic connections achieve significantly higher marks. You cannot just look at a vector in isolation. You have to connect vector geometry to trigonometry, or link it up with coordinate geometry. That cross-topic referencing, that acts as our high-propulsion fuel for achieving those elite evaluation metrics. It proves to the examiners that you don't just know the definitions, you understand how the entire mathematical machine works as a synchronized whole.
Act 2, Procedural Framework. Let's start engineering the flight path.
Down in the telemetry bay, Alex and Sam are constantly debating how to handle complex, multi-part past paper questions under strict time pressure. But the only way to avoid a system overload is to rely on the strict, standardized procedural sequence. Step 1. Identify key elements. You need to extract the relevant position vectors right out of the text before doing anything else. Step 2. Apply relevant principles. This is where you decide strategically if you are using vector addition or subtraction to find that displacement vector. Step 3. Execute your analysis with crystal clear working, no skipped steps. Step 4. Verify your results against the given geometric parameters. And Step 5. Present your final data in the appropriate format requested by the command word. Synchronizing these 5 precise steps ensures you navigate the turbulence of the exam efficiently without burning up your time fuel.
Let me show you exactly what a system failure looks like versus a perfect launch. There is a massive structural difference between a descriptive and an evaluative approach. A descriptive trajectory is basically a low-altitude flight. This happens when a candidate just dumps isolated vector definitions onto the page without any context. Maybe they successfully perform a basic scalar multiplication, but they completely fail to explain what that result actually means in the context of the specific geometry problem. They crash. Conversely, the evaluative pathway is a high-propulsion launch. It involves rigorous, systematic processing. It means questioning assumptions, applying those crucial cross-topic connections we talked about, and drawing firm, evidence-based conclusions, particularly when the examiner's command word demands it. This is the only way to secure the top-tier marks.
Initiating peer telemetry coordination, we're diving into the method mark lifeline.
Warning klaxons are blaring on the console right now, and this is an official examiner alert. Show your working method. Marks are literally your emergency safety net, your ultimate lifeline. Alex over in Propulsion sometimes tries to rush calculations in his head to save time, and it almost always results in a catastrophic point loss. Listen, if you make a tiny careless arithmetic error in your scalar multiplication, but you explicitly write down your formula, show your exact substitution, and demonstrate the correct mathematical process, the examiner will still award you those precious method marks. You survive the error. But attempting these calculations mentally and just writing down the wrong final answer, that yields absolutely 0 marks. The system fails you completely.
I am projecting the data comparison on the main monitor now. The difference between a flawed approach and a top-band approach is incredibly stark. Look at the left side. Relying on mental math without written steps, giving the final answer only, and leaving your outcomes unverified, that consistently leads to a crash trajectory. Now look at the right. The top-band approach utilizes a step-by-step deconstruct, solve, and evaluate mechanism. It relies entirely on logical steps with incredibly clear working. It means using proper headings, verifying the reasonableness of your outcome, and utilizing flawless vector notation. I'm talking about drawing the correct arrow over the AB or clearly underlining your lowercase letters. Those little details stabilize your entire flight.
We are initiating a mid-mission hold. Navigation booster deployed.
Launch trajectory hold. I am freezing the telemetry console for just a second. Before we deploy our final top-band structure to clear orbit, you need to optimize your own educational flight deck. Take a second right now to hit the subscribe button for Ace the Exams and enable all your notifications. We engineer these weekly, flight-tested exam hacks designed to get you maximum marks across all Cambridge levels, from IGCSE up to AS and A levels. Do not fly into your exam season blind. Lock in with our proven strategies and secure your payload.
Okay, we just experienced a simulated data loss in our response paragraph, threatening a mission termination. But we are overriding the console and deploying our structural power-up, the deconstruct, solve, evaluate framework. When dealing with complex vector problems, this framework ensures absolute stability. Let's rewrite our response live, line by line. First, identify the given information. You must write down the position vectors exactly as they are given in the paper. Second, break it into logical steps. Explicitly state whether you are deploying vector addition or subtraction. Third, solve systematically. Apply your scalar multiplication carefully, component by single component. Fourth, check for reasonableness. Look at your result and ask, does the direction of this final vector actually make geometric sense? And finally, make justified recommendations or conclusions based entirely on your mathematical evidence. That is how you stabilize a failing structure.
Act 3. Hazard Evasion. We are launching the Interactive Radar Sweep Challenge.
I am handing the console controls over to you. Where do candidates most commonly trigger system failures in vector questions? Think about all the source data we've reviewed from the official Cambridge Principal Examiner reports so far. Is the primary hazard the calculation itself, the notation, or the underlying logic? I'm initiating a visual radar sweep right now. Look at your mental data. Let's see if we can extract the single highest-yielding core trend before the system resets.
Sweep complete. I'm highlighting the discrepancies on the digital indicator. Here are the top 3 examiner warnings. The exact parameters where students bleed marks. Number 1. Answers are often way too vague. In vectors, if you just vaguely state the lines are parallel without actually showing the mathematical proof that one vector is a precise scalar multiple of the other, you instantly lose the mark. Number 2. Students completely forget to check format, presentation, and proper headings. Writing a coordinate when the command word specifically asked for a column vector is a massive common failure. And number 3, answers are not specific to the context given. Sam over navigation is always pointing this out. You must tie your geometric proof directly back to the specific shapes or coordinates provided in the initial problem prompt. Generalizations will cause your flight to plummet.
Here is a critical boundary coordinate that Sam noticed candidates miss all the time. When a question asks you to evaluate or compare geometric models using vectors, a flawed comparison stops at only identifying the similarities between the vector relationships. It's a half-finished job. An elite, full-mark comparative analysis requires identifying the similarities and the differences. You have to build a complete picture. It requires strategically using comparative connectives, mathematically supporting each and every step with concrete evidence from your vector addition or subtraction, and then drawing firm, unshakable conclusions about their relative geometry. If you leave out the differences, your structural integrity fails.
Act 5, Summit reached. We are initiating our flight completion outro.
Alex and Sam are confirming a successful launch sequence. The propulsion meters are peaking at a maximum A-star reading. To ensure you can replicate this success on your own, I am distilling this entire session into 3 universal launch rules. Rule 1, the 3-step question scan. Before you even touch your pen, decode the command words and extract every single piece of relevant vector data. Rule 2, the fuel budget allocation. You have to manage your timing. Do not burn 10 minutes of fuel on a simple 2-mark addition question, and absolutely do not rush a complex 6-mark geometric proof. Balance the burn. And Rule 3, the post-launch system review checklist. Always verify your final results for geometric reasonableness, and strictly check your vector notation and formatting before moving on.
Mastering vectors is not just about moving abstract lines around on a piece of paper. It is about understanding the invisible mathematical geometry that holds physical space together. The question now is, how will you apply that precise zero margin for error perspective to your next exam paper? Which Cambridge subject and level are you preparing to conquer next? Is it IGCSE O-Level, AS, or A-Level? Drop your target in the comments below. Make sure you hit subscribe for Ace the Exams, click that notification bell so you never miss a payload, and stand by for your next briefing. Flight Director, signing off.